Let's take the limit as x approaches 0 of sine 5x over 3x. Now we saw in the previous video that the limit as x approaches 0 of sine of g of x over g of x equals 1, where g of x is a function such that the limit as x approaches 0 of g of x is 0. Now if g of x happens to be 5x, well, the limit as x approaches 0 of 5x is 5 times 0. 5x is a continuous function at 0, so we can, well, it's a continuous function everywhere actually. There are no breaks in it, so we can just plug 0 in for x. And if we do that, we get 5 times 0, which is 0. So 5x satisfies this condition here. So we need to write this thing in the form sine 5x over 5x. So it'll have the form sine g of x over g of x, where g of x is 5x. So what we do is we just write in underneath here 5x. So we're sticking a 5 in. So I've removed the 3. I'll take the 3 out here. But to compensate for putting in this 5, we have to put a 5 on top, so that the 5's obviously cancel and we just get back to this thing here. So of course you must check that this equals this. But now you see we have the limit as x approaches 0 of something of the form sine g of x over g of x, and you can see that the limit as x approaches 0 of 5x is 0. So we're satisfying both of these, which means that when we take the limit as x approaches 0 of this thing, we will get 1. Now the limit of a product is the product of the limits. So the limit as x approaches 0 of this thing is 1. The limit as x approaches 0 of 5/3 is 5/3, because 5/3 is a constant, and the limit of a constant is just a constant, whether x approaches 0 or indeed any number. So our answer is 5/3. Now you can always check this by going to your calculator and picking a number very close to but not equal to 0. This thing isn't even defined at 0. If we plug 0 in for x, we get sine 0 over 0, or we get 0 divided by 0, which is indeterminate. So pick a number very close to 0. So we want to plug that in for x here. So sine of 5 times this, well, that's 0.00005. And we have to divide by 3 times 0.00001. That's 0.00003. So make sure your calculator is in radian mode, and we want to get the sine of 0.00005 and divide that by 0.00003. So we should get a number close to 5/3. Well, 5/3 is the same as 1 2/3, or 1.66 recurring. So you see we do indeed get a number that's very close to 5/3. You might have noticed a pattern in this limit. This limit turned out to be 5/3. So in general, suppose our function has the form sine ax over bx, where a and b are any numbers, although b can't be 0 because we don't want division by 0. Then we might expect that this limit is equal to a over b, in the same way that this limit was just 5/3. Okay, well, we stick an a in here, and to compensate we have to put an a up here. So you can check that these a's cancel out, of course, and we have b times x, giving us back bx in the denominator here. So the limit of a product is the product of the limits. Now this thing here is going to be 1, because ax has the property of going to 0 as x approaches 0. So a of x is our g of x in general, okay, as we saw before. So as long as this thing has the property of going to 0 as x approaches 0, then we can say the limit of sine ax over ax is 1. And the limit of a constant, well, a over b is a constant. The limit of a constant is just a constant, regardless of what x approaches. So we get 1 times a over b, which is indeed a over b, as we suspected. Now let's suppose we take this example here. Well, let's just rewrite that. What I can do is I put a 5x squared here. So we take out the 3 and we put a 5 up here. So these 5's cancel and we get back what we had. Now, so what have we done? We've tried to make these two the same. So 5x squared is our g of x. And notice that if we take the limit as x tends towards 0 of 5x squared, well, we actually get 0. 5x squared is a continuous function, no breaks everywhere, in particular no break at 0. So we just plug 0 in for x, and we get 5 times 0 squared, which is 0. So that's the important thing. So we need to ensure that this thing here that's highlighted goes to 0 as x approaches 0. Since that's true, we get the limit of a product is the product of the limits. So we'll have 1 times the limit of 5/3. Well, that's just 5/3. So our answer is 5/3. Now let's take this example here. This time we don't have an x squared in the numerator. Now if we've no idea of how to do this, we can go to our calculator and plug in a very small value for x. Let's say 0.0001 and see what we get. Well, we're going to get sine of 5 times 0.001. That's 0.0005. And we have to divide this by 3 times 0.0001 squared. So we want the sine of 0.005. So we put in 0.005 in radians, get the sine, and we have to divide that by 3 times 0.0001 squared. Notice that we're getting a large value here. Let's just go through this without plugging in values of x close to 0. So again, we want to have this thing in the denominator underneath sine of 5x. So we have to write 5x in here. So now it's got the form sine g of x over g of x. And of course 5x goes to 0 as x goes to 0. So that's okay. Now how about the 3x squared? Well, we need to have an x here to get back the x squared. And how do we get a 3? Well, we need to cancel that 5 out, so we put a 5 up here. And we have a 3 here. So now you see the 5's go and we have the 3x squared underneath. So the limit of a product is the product of the limits. We know that this thing is going to be 1. Now what about this thing here? Well, as x approaches 0, 5 over 3x is going to get larger and larger. As a matter of fact, we can make 5 over 3x as large as we like by taking x sufficiently close to, but not equal to 0. So we could say our limit is infinity. And, you know, if you take a value of x that's even closer to 0 than the one that we did on the calculator, you'll get a larger number still. The closer x is to 0, the larger this quantity will be. It'll get larger and larger. Of course, I took a positive number for x. I took what was 0.0001, I think. It was positive. We got a large positive number. We got plus 16,666. But if you take a negative number, you'll get a large negative value. So I won't do that, but you can get a large positive or negative value depending on whether x is approaching 0 from the left or the right. So to be more accurate, we should put in plus or minus infinity here, depending on which way we are approaching 0. When we take the limit as x approaches 0, we mean x can approach 0 from both sides. So we could get a very large positive or a very large negative number. Finally, let's take this one here. This looks quite different from the previous examples. The limit as x tends towards 0 of the tan squared 2x over 3x squared. What we will do is write tan of 2x as sine 2x over cos 2x. So tan squared 2x is got by squaring this, sine 2x over cos 2x times itself. So that's sine squared 2x over cos squared 2x. Now, we have sine squared 2x on top. Well, I'll write that as sine 2x times sine 2x. And that's divided by cos squared 2x, so I'll write that as 1 over cos 2x times, well actually I'll write it as just 1 over cos squared 2x. Now all of this is divided by 3x squared. Now, In order to use this result up here, we want 2x to appear in the denominator. So, well, I'll just stick it in here, and we can compensate by multiplying out here by 2x, so they cancel out. Okay, so here's a function of the form sine of g of x over g of x, where g of x goes to 0 as x goes to 0. That's 2x indeed does go to 0 as x goes to 0. Okay, we need to put a 2x here, so we have a second function of this form. So both this and this will go to 1 as x goes to 0. That's good. But we have to compensate by putting another 2x here to cancel this 2x. Now, from here we get x times x is x squared, and that cancels with this x squared here, so we can actually cancel these out. So we have x squared above the line, and we have x squared underneath the line. You see, we end up with 4 over 3, so we could multiply all of this thing here by 4/3. So the important thing is to make sure that this thing is equal to the previous bit, and you can see that it is. We have 2 2's are 4. They cancel out, and you get the 3x squared in underneath. Okay, so you could say that we have a product of 4 functions here, and it can be proven that the limit of a product is the product of the limits. So this first limit here is just 1, because we're getting the limit of something of the form sine of g of x over g of x, where the limit as x tends to 0 of g of x is 0. Similarly, this one here, well, this one is identical to it, so both of these are 1. Now what about this thing here? Well, the cos function and also the cos squared function is continuous for all values of x. There are no breaks in this function. Indeed, 1 over cos squared 2x is continuous everywhere. There are no breaks in it. So to get the limit as x approaches 0, all we do is we just plug 0 in for x. If you do that, you get 1 over cos squared of 0. Well, cos of 0 is 1, so obviously cos squared 0 is 1. Okay, if you plug 0 in for x, you get 2 times 0 is 0. The cos of 0 is 1, the cos squared is 0 is 1, so we get 1 divided by 1. And finally we have the limit of a constant. Well, that's just equal to the constant, which is 4/3 in this case. So our answer is 4/3. As a check, let's pick a number x that's close to 0 and plug it into this here. So we have 2 times 0.001, that's 0.002. Let's get the tan of that number, and let's divide it by 3 times 0.001 squared. Something went wrong there. Let's try that again. We have 0.002, and we want to square this number. Okay, so we need to take this and divide it by 3 times 0.001 squared. At last we get a number that's very close to 4/3, 1.33333688, etc. So that's very close to 4/3, so it looks like we're right.